Following its isolation and characterization in 2004, graphene has become a staple in condensed matter physics research. Graphene is constituted by a single 2D layer of carbon atoms. It has remarkable properties with a plethora of potential applications, namely in healthcare and electronics. It is the strongest material ever tested, 100 times more than steel, and it is a transparent, efficient conductor of both heat and electricity. Moreover, it is also strongly diamagnetic and hosts superconductivity under certain conditions. Several challenges remain on the application side. Single-layer graphene is gapless, while bilayer graphene has a tunable but limited gap when compared to standard semiconductors like silicon or germanium. Better switching capabilities would be desirable to design, for example, transistors made out of graphene. Furthermore, graphene has been predicted to undergo transition to a superconducting phase. However, limited success has been achieved in attaining it. The existing methods seem to compromise other desirable properties. Transition metal dichalcogenides, or TMDs, are graphene-like layered materials. They have a hybrid, unique electronic structure. While the bulk is semiconducting, the edges are metal-like when zigzag-shaped. The intrinsic gap that is absent in monolayer graphene might help overcome graphene's poor switching drawback. Additionally, hole-doped TMDs, where the charge carriers are positively charged holes, are good candidates to host topological superconducting phases, arising due to electron interactions. Ferromagnetism and spontaneous valley polarization are also expected, the latter being promising in the development of devices belonging to a new concept in electronics. We will simulate electron correlations, playing a key role in TMDs. Quantum Monte Carlo is a natural method to tackle the problem. It allows us to capture the effect of interaction satisfactorily, going beyond, for example, a mean field approach. In mean field, we make a radical approximation. Every electron interacts in the same manner with an external model entity consisting of the sum of the effect of all other electrons. Monte Carlo is a sampling method. It is particularly useful when the number of possible configurations of the system is exponentially large. Suppose you have people sitting next to each other in a circle. Each person, I, has a happiness number plus or minus 1. Some are friends, some are not. A person is either happy, s equal 1, or sad, s equal minus 1, and people are happier when sitting close to friends. Thus we would like to minimize sadness, h. This is called the Ising model. Note that a big circle with lots of people, L, would allow 2 to the L different configurations, which is in general a huge number. Ideally, everyone is friends, so s equal 1 for everyone. Physicists call this the ground state. More complex models might have different ground states with both happy and sad people. It is not always possible to please everyone. A general configuration has both happy and unhappy people. Nature favors low energy, happiness. If you sit people randomly next to each other, they will change seats until an optimal configuration is found, equilibrium. In classical Monte Carlo, one simulates the oscillations between configurations of a system due to thermal fluctuations. QMC tries instead to simulate the effects of quantum fluctuations. Crucially, Monte Carlo applies importance sampling. A scheme is implemented to sample only the most representative out of all possible configurations. Diffusion QMC takes advantage of the fact that the quantum equation for the evolution of configurations may be thought of as a diffusion equation. The latter explains how a drop of milk makes your coffee gradually change color. The method relies on the fact that less likely configurations of higher energy are filtered out at a faster rate due to the nature of the diffusion. Auxiliary field QMC uses a mathematical transformation to map a quantum problem in d dimensions to a classical problem in d+1 dimensions. Amazingly, the second one is easier to solve computationally. To sum up, we will simulate a two-dimensional material using QMC, a state-of-the-art computational method that captures the effect of electron interactions accurately. These are expected to be responsible for promising phases in a class of materials called TMDs. Understanding the effects of electron interactions and the resulting phases allows us to control quantum states that could lead to a new generation of innovative, more powerful electronic devices.